Alright, so in this video I'm going to be explaining another important article about domain adaptation. The title is Beyond Sharing Weights for Deep Domain Adaptation. So this article in 2016. The performance of a classifier trained on data coming from a specific domain typically degrades when applied to a related but different one. While annotating many samples from the new domain would address this issue, it is often too expensive or impractical. Domain adaptation has therefore emerged as a solution to this problem. It leverages annotated data from a source domain in which it is abundant to train a classifier to operate in a target domain in which it is either sparse or even lacking altogether. In this context, the recent trend consists of learning deep architectures whose weights are shared for both domains, which essentially amounts to learning domain invariant features. Oh, by the way, when we say features, it is good to decouple. So some part of your feature space, this part, I call it invariant, feature invariant. The other one is domain specific, and the first one is invariant. It means that it is shared, but among all, it is something that is inherited from all domains, but the domain is specific, as the name suggests, is just specific to the domain. That is the particular characteristics of each domain. So it's always good to decouple the feature space so that your model becomes more explainable, more interpretable. So in this context, the recent trend consists of learning deep architectures whose weights are shared for both domains, which essentially amounts to learning domain invariant features. We show that it is more effective to explicitly model the shift from one domain to the other. To this end, we introduce a two-stream architecture where one operates in the source domain and the other in the target domain. In contrast to other approaches, the weights in corresponding layers are related but not shared. We demonstrate that this both yields higher accuracy than state-of-the-art on several object recognition and detection tasks and consistently outperform. So what is important is the weights in the corresponding layers are related but not shared. So this is our two-stream architecture, that one stream operates on the source data and the other on the target data. Their weights are not shared. Instead, we introduce loss functions that prevent corresponding weights from being too different from each other. So here we have domain discrepancy, and we do it for source and loss. You see, there is a loss in each layer, for each layer. And this is the regularization. So the core idea of the method is that for a deep network to adapt to different domains, the weights should be related yet different for each of the two domains. This constitutes the major advantage of our method over the competing ones. The first stream operates on the source data. So here there are two streams, the source stream, the target stream. And here is saying that the first stream, which is the source, operates on the source data and the second on the target data, and they are jointly trained. They are trained jointly. While we allow the weights of the corresponding layers to differ between the two streams, we prevent them from being too far from each other. So we don't want the weights of them to be too far to each other. So that's why we have a regularizing loss that keeps them almost near each other. So it's interesting. So this reminds me continual learning and elastic weight consolidation, those things which I have explained on my playlist for continual learning. While we allow the weights of the corresponding layers to differ between the two streams, we prevent them being too far from each other. So I said this. Now, additionally, we use this maximum mean discrepancy between the learned source and the target representation. This combination lets us encode the fact that while different, the two domains are related. So we have source and target images, and we have their corresponding labels of source and labels for target. But to handle unsupervised target data as well, we assume without loss of generality that target samples are ordered such that the only first target ones have valid labels. And in the unsupervised setting, there are 0. So theta of source, parameters of target and source, the weight and biases, and the J's. These are J's layer of source and target streams. And we train the network by minimizing the loss function of the four: loss of source, loss of target, and maximum mean discrepancy. And what is this one? This one is just R of theta source and target that I will explain. So these are the weight and unsupervised regularization that I will explain. And this C here that you see in both source and the target, C is a standard classification law. So whatever you know from classical machine learning, that's it. But the second encodes the maximum mean discrepancy. So that R that I said, it's a regularizer. It's just L2 norm between source and target. Or you can see it in an exponential form. It's the same. This one is the same. So this is called weight regularizer. But in addition to regularizing the weights of corresponding layers, we aim final representation, the features before the classifier is domain invariant. To this end, we introduce RU to minimize distance between the distributions. So MMD measures the distance between the mean of the two sets after mapping each other to I've explained this reproducing kernel Hilbert space in a different video, which is very interesting and important. It is developed by people in Max Planck in Germany many years ago, but it's very, very important. But many people often overlook that, unfortunately, because they think that it's too theoretical, but it's very, very important. In our context, F sub I is a feature representation at the last layer of the source stream, and F sub j of the target stream. And then we can see because they are features, so we can see the MMD between the features. And this phi is just the reproducing kernel Hilbert space. So our features are in the Hilbert space. So this mapping is typically unknown. So if we expand equation 8, and we always use kernel trick when we talk about the things, we never go directly, it's very difficult, but if you just kernel trick, you see that, it's just something that we know. The kernel of the two features are easy to calculate. If you just reproduce this If you just work on this formula, and then you will see the 9. So we make use of a standard radial basis function kernel. A special kind of kernel is called RBF, or reproducing or radial basis function. So to learn the model parameters, we first pre-train the source stream using source data only. We then simultaneously optimize the weights of both streams according to the laws, using both source and target data, with the target stream weights initialized from the pre-trained source weights. Note that this also requires initializing the linear transformation parameters of each layer, and we initialize these values equal to 1 and 0, thus encoding the identity transformation. All parameters are then learned jointly using backpropagation with Ada delta algorithm. So depending on the task, we use different networks to provide a fair comparison. For example, office benchmark, we adopt AlexNet architecture, and you see our UAV dataset. You see synthetic and real training, and on the bottom you would see the real samples. And we use synthetic data. The data is very expensive, but you synthetically generate it. For example, these synthesizers that create synthetic images in graphics are very important for example, just self-driving cars or other application. So these are synthetic images in the source domain. Because there are many of them, we can generate tons of them, billions of them. But these real images are very expensive to capture these images. So that's why your target is usually these real images. And you see different accuracies from different sources going to different targets. And you see this one is the worst case. So it means that this source and this target, this combination, it has something that is difficult, that is not fully observed and explained by the model.